Okay, hello everyone. Uh, I know that we were scheduled to have a practice exam for our midterm two, but as you know, we are like running behind the planned schedule, and we have still not finished the topic of CPU scheduling while we were supposed to by this time complete the process synchronization, which is the next topic after CPU scheduling. So that's why I decided to not have a practice exam in during the lecture hours. What I will do is that I will release the practice exam and its solutions separately on the canvas, and you can try to solve it on your own uh, out of the class hours or lectures hours. And then you can, after solving it, you can have a look at the solution to understand whether you did it correctly or not, right?
Okay.
So in this way, we can like at least save some time and we can try to cover the syllabus. Okay. So with that, for second part of this lecture today, I don't have those online, Zoom supported quizzes or polls, but I will strongly encourage you to ask questions if you have, right? Or if there is some example in the slides, I will give you some time and I will ask you to do on your notebook, right? But I am interested in covering the material as much as we can. So will we still be having our exam Tuesday, correct? Yeah, yeah. That you will be having the exam. There is no change in the date of the midterm two exam. What I'm saying only is this, that today we are not solving a practice exam. I will release practice exam and you can do it offline. Okay. Okay. So I'm skipping this first slide. So okay. So last time we were talking about we were covering the scheduling algorithm. We had covered first come first serve. We have covered shortest job first, shortest remaining time first algorithm, and also round robin algorithm, right? So now we are going to talk about a category of scheduling algorithms which have priority based scheduling. So a priority, what we can do is like to with each process we can associate a priority, and how by specifying a priority number which is just an integer, and it tells what is the priority level of that particular process, right? So uh, then the priority based scheduling algorithm, what do sorry what they do is that the scheduling algorithm look at the priorities of all the ready processes and pick the one which has the highest priority for scheduling or for running on a core, right? So different operating system use different mechanisms. So for example, some operating system can say, okay, we are using integers to specify the priority, but smaller the value of an integer, higher will be the priority. But in some other operating system, it can be a case that higher number means higher priority. For example, in Linux, you have higher integer number mean the process has the higher priority. So for example, in Linux, you can have priority in the range of 0 to 99. So if for one process, let's say the priority number is 10 for process A, and process B, it is 20. So it's mean process B has higher priority than process A. Okay. But in some other systems, they can use the reverse mapping, which is like process A is more has more priority than process B, because process A has integer value of 10 and process B has integer value of 20. So it depends. But in Linux, it is higher the number, higher the priority. Okay, so priority scheduling can be of two types. Preemptive priority scheduling, where a higher priority process can preempt a currently running process with a low priority, right? So if process A, let's say, has higher priority and process B is currently running, and then process A becomes ready, so process A will preempt process B because process B has lower priority. Uh, Another version of priority scheduling is where we don't imply the we don't use the preemption. So for example, let's say process A has higher priority than process B, and currently process B is running. While process B is running, process A becomes ready, but process A will not preempt process B because process B is already running. So shortest job first is a priority scheduling algorithm, but it was non-preemptive. How it is a priority scheduling algorithm? Because remember, in shortest job first, what we were doing whenever we want to decide or whenever we want to pick a process from the ready queue, we look at the process which has the shortest CPU burst. So the process which has the shortest CPU burst has the highest priority. So it's mean that it is a priority based scheduling algorithm, right? So the priority is coming from the length of the CPU burst of a process. However, shortest job first was non-preemptive. So for example, if process A is running and its CPU burst is, let's say, remaining CPU burst is, let's say, 10 time units, and then process B becomes ready and the CPU burst of the process B is 5 time units. So process B will not preempt process A. Process A will complete its execution, right? On the other hand, shortest remaining time first algorithm is a priority based scheduling algorithm, but is a preemptive one, right? We have seen this algorithm in the previous lecture, and again, the priority is coming from the fact that which process has the shortest remaining CPU burst, and also a process which has higher priority can preempt a currently running low priority process. Any questions here? I don't want to go into this detail because we had in the previous lecture, we had a couple of examples on SRTF and SGF, right? Okay, so we have some polls here. Okay, no questions at the moment. Okay. Uh, so let me go to the poll OS. Yeah, this one. Yeah. No, 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 no. And the poll, not this one. Yeah, it is one, right? Yeah, this one. Okay. Yeah, do this in 60 seconds. And if you can do faster, it will be better. Okay, I'm stopping it here. Let me walk you through these questions. Typically, SJF and SRJF provide better response time than FCFS. That's correct because FCSFS waits for, first process to complete execution and then the second one goes on. But SJF and SRJF, they look at they prioritize the processes which have shortest burst time, right? Second question, like SJF and SRJF, are our needs estimation mechanism for bus time? No, this statement is false. RR don't needs it is not dependent upon the CPU bus time. It is dependent upon it performs scheduling based on the quantum at the time slice, right? What is the next question? Three, RR provides better response time than FCFS. That is true. Why? Because as I said earlier, in FCFS, we wait for the process that arrives first to complete before we can schedule any other process that arrived later than the first process, right? But that is not the same in RR because in round robin, we are using time slice. Okay. Four, shortest remaining time first is a non-preemptive scheduling algorithm. This is false, as we have seen examples in the previous lecture. it is a preemptive algorithm. If process A is running and its remaining time is, let's say, 10 time units, and then process B becomes ready and its remaining time is 5 time units, so process B will preempt process A. Okay, SJF is not a priority algorithm, false. It is a priority algorithm, and the priority is based on the CPU bus time, right? So we give priority to a process which has the shortest CPU bus time. Okay, SGF is a preemptive priority scheduling algorithm. This is false. SGF is a priority scheduling algorithm, but it is not a preemptive scheduling algorithm. It perform preemption. Okay, so let's do an example here now. So suppose you have these processes A, B, C, and D with the given arrival time and CPU bus time and the priorities 32011, right? Draw a scheduling chart and find finish time of each process. Use non-preemptive priority scheduling. So you need to do priority scheduling, but non-preemptive one, okay? So, and you need to find the finish time of each process. Okay, I'm going to OneNote to do it quickly. Okay, new page. Week 10, day 2. By the way, this OneNote, is it? I have embedded a link for it in the Canvas page. Are you guys available to access it? Like in hours outside the class time?
I haven't tried yet, but that would definitely be helpful. I'll look into it.
Okay.
Yes, I tried it. It works.
No, okay, thank you. Thank you. So you need to find finish time and we need to use preemptive priority scheduling. There is some I'm transcribing. Okay, that's okay. Okay. So uh yeah. Mm, yeah. So again, let's first, or maybe I need to calm down. I know I am trying to save the time, but I don't need to panic. Okay. Uh, so I'm just first putting the arrival time 0, 5, 10, 25, and 30. And this is arrival time of A, B, C, D, and E, right? So at time 0, no one is arrived, only process A is there. So I schedule it, right? And I keep it running and for 5 time units, right? And so then its remaining CPU burst is now 15. And then at 5 B arrives. Now I select among A and B, whichever has the highest priority. And here I'm assuming lower the number, higher the priority. Okay, I'm assuming again lower the number, higher the priority. So B has the higher priority. Okay, so now I'll allow B to run until 10. So for 5 time units, so its remaining time is now 10. And then at time unit 10, C arrives. Now I need to select between A, B, and C. So C has the highest priority. So I allow C to run uh, until 25 time unit, until 25. So its remaining time is now 5 here, right? And then D arrives. So D has the priority of 1, right? So I continue running C for 5 more time units. Oh, sorry, not here. 30, right? So now its remaining time unit is 0, right? So I am done with C. Okay. Now at 30, I have A, B, and D, A, B, D, and E ready, right? So now I select the one which has the lowest priority. So D and E, they both have the same priority. I can go with any one of them. Let's say I select D, right? So if I select D and I allow D to run for 15 time units. So 30 plus 15, 45, right? And then I am done with D. Now I need to select between A, B, and E. Now E has the highest priority. And I allow it to run. It has 20 CPU bus, so it runs up to 65, right? Now I am done with D and I need to choose between A and B. So B has the highest priority and its remaining bus time is 10. So it runs up to 75. Then B is also done and I have only one candidate, which is A. So A runs for 15 time units, so which is, it ends at 90, right? So the finish time, I'm just writing here the finish time of A is 90, B is 75, C is here 90, 75, C is here 30, D is 45, and E is 65. Is it clear to everyone? Clear. Okay, good. Thank you. So, okay, so this is just the solution which I have shared with you. So here we are doing the non-preemptive priority scheduling. So we are writing A, and here we are assuming that each letter is representing 5 time units. Okay. Okay, no, this will be different. This will be different because here in this solution, we have assumed that higher the number, higher the priority. But the solution I showed you on the on one node, there I assumed that lower the number, higher the priority. Here, let me just put a note so that it you don't get confused. Okay, so where is it? Yeah, this one. Higher the number, higher is the priority. But the solution I showed you on OneNote, it was assuming that lower the number, higher the priority. Okay. Don't get confused. Uh, Someone sent a message. So we just assume any time unit, like you just assume 5 time unit. So no, here like see here we are assuming that one letter is I just wanted to, instead of in this solution in this slide, instead of drawing the Gantt chart, I just wanted to show the schedule by putting the letters. Now, how long a process runs, I show it by putting letter. So one letter represents 5 time units. So here I'm saying initially that A is running for 20 time units. And after that, so its CPU bus is finished, then C runs. And the CPU bus of C is what? 20. So that's why C also has 4 characters. C, 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 C. So 4 times 5 is 20. Okay. So it is just an alternative way of representing the schedule. But I mean, I showed you on the one node using Gantt chart. Okay. Okay. Now we have the same result, same processes here, A, B, C, D with same arrival time, same CPU burst, and same priority. Draw the scheduling chart and finish time of each process use by using the preemptive priority scheduling. Earlier, what we were using? We were using yeah, my mistake. My mistake. Sorry. That is what when you when you try to rush the things. So the example I showed you on OneNote, there are two important points to consider. One, I assume that lower the number, higher is the priority. One. Second, it was I was supposed to do the non-preemptive one, but I did actually the preemptive one. How? Let me go back to the OneNote and explain. So here C, it is preemptive because A was running, and then when B arrived, so since B has highest priority, it preempted A. So it is preemptive one. Okay, so I did this one. Let me also put a note here for you. So here assumption here, lower the number, higher the priority, and this solution is for preemptive priority scheduling. Okay. So now it requires me to also do the non-preemptive variant so that it becomes clear to you. Yeah, instead of like saving time, I am wasting my time. Okay, so now let me do it again. Okay, do the solution for non-preemptive priority scheduling. Okay. Okay, let me simply copy over uh, this one, the same table. Okay, and just to like cover all the cases here, I'm assuming now higher the number, higher the priority. In exam, if you have a question, I will specify how to interpret the numbers. Okay, and here now we are using now we are doing non-preemptive priority scheduling. Okay. By the way, should you guys should have interrupted me when I was doing the previous one, like by saying, Professor, it is not non-preemptive, it is preemptive. Okay, so let's do now this one. Okay. Again, I am just putting first the arrival times. So 0, 20, no, not 20. 0, 5, 10, 25, 30, right? And okay, now at time A, we don't have any other candidate, only A is ready, right? And it has CPU burst of 20, right? So we will allow it to run for 20 time units. Although even like, let me put here A, B, C, D, E. I will allow it to run to 20 time units, even though B and C are becoming ready, but at 5 and 10. But I am using non-preemptive variant. So B and C, although they have they have anyway, they have lower priority, so they cannot preempt. Even if they had higher priority, they cannot preempt because we are using non-preemptive variant. Okay. Someone asked a question. We are learning, we wouldn't know to interrupt. Okay. Okay. Uh, okay. So Uh, so A is equal to 0 to 20. So here we allow a process A is done now, right? Now then at 20, once we are done, we need to decide. So which processes are ready now? B and C. So we need to choose between B and C. So who has the higher priority? Remember, we said higher the number, higher the priorities, right? So B has higher priority. So we are selecting B, and B will run for 15 time units. So 20 plus 15, uh, 35, right?
Yes, 35.
Yeah. So B, okay. So now, in the meantime, 25 and 30, at 25 and at 30, D and E become ready. But anyway, they have, first, we are using non-preemptive variant, and second, they also have the lower priority, so we don't care. Okay. So now at 35, we need to decide again who will run, right? So when we at time 35, which processes are ready? So we are done with A, and by the way, at this time point, we are done with B. So C, D, and E are ready, right? So we pick the one which has the highest priority. Now D and D, they have the same priority. So we can select any one of them. Let's say I select D, right? So D will run for 15 time units again. So if D runs for 15 time units, so it will be 35 plus 40, 50, right? So, okay. And then after that, C and E are ready. So I need to select one which has the highest priority. So E has the highest priority and E runs for 20 time units. Okay. So, no, sorry. So it runs for 20 time units. So
Yeah, that'd
50
be
plus
70.
20, 70. Yeah. So, and then I'm also done with E. Now only C is ready. So C will run for 20 time units. So 70 plus 20 is 90, right? And now here I can write finish time. So the finish time of A is 20. Finish time of B is 35. Finish time of C is 90. Finish time of D is 50. And finish time of E is 70.
I had a question about the slides.
Yeah, good.
Uh,
Slides are the example on OneNote.
so I don't actually see D2 W10D2. I see W10D1 on the 28th, but then there's the practice exam one and then the midterm exam, but there's
Yeah.
nothing that actually says D2. It's just D1.
Are you are talking about schedule, syllabus document?
Yeah. So like if you scroll down,
Yeah.
it's, the slides in 10 is that's D2. Or no, sorry, that's D1, not D2. I'm trying to find D2.
You're talking about slides. Okay. Lecture slides. So here they are, lecture W10D2 planned.
Okay.
And I have also embedded them on the syllabus page here. By mistake, I deleted the date, but I will fix it after the lecture. But slide link is available here.
Well, no, that slide link is to D1, I think.
Oh,
At
okay.
least that's
After the lecture, then I will fix the link. I will fix the link then. Maybe by mistake I did it, but I will fix it
Oh,
after.
wait, I see the problem. On my end, it says practice exam midterm 2 there. So I don't think it's actually updated yet.
Just refresh your browser. But you can see from my screen for the time being, and after the lecture, I will take care of that. Okay.
Okay, got it. Thank you.
Okay. So I'm skipping this poll quiz 2 because I did it on the OneNote, right? So this is again I modified it because here it wanted us to do preemptive one, but I did the non-preemptive one because I did preemptive one already. So the important thing is that you know what is the difference between preemptive and non-preemptive one, right? So we had two examples. First example using preemptive one and the second example using non-preemptive priority scheduling. Okay, now priority scheduling, it can end up having some issues, and one of the issue is like a process can suffer from the starvation. What does it mean? It means that there can be a situation where the higher priority, the number, for example, let's say you have 100 processes, right, which are ready, and out of those 100, let's say 90 processes are have the higher priority. Let's say you have only two priority level. Let's say I'm saying 1 and 2, and higher the number mean higher the priority. So 90 processes, they have priority number of 2, and 10 processes have priority number of 1. Now what will happen, that are those 10 processes which have priority number of 1, they will not be able to run unless all the 90 processes that have priority number of 2, they are completed, right? Only after that the processes with lower priority can run. So it's mean that they are suffering from starvation, right? And there can be a case like, let's say if there is a situation that higher priority processes, uh, they are newly generated, like they keep arriving in the system, and then you will end up in a situation where low priority process will never get a chance to run. Okay, so that is a problem with the priority scheduling, that low priority processes, they may never execute because there is always a higher priority process ready to run. Okay, so what is the solution to this problem? The solution is known as aging. So aging is a mechanism where what you do is that as time progresses and a lower priority process is not getting a chance to run, so as the time progresses, you increase its priority. So just like the example I gave you, let's say there are like 10 processes which are waiting. So every time, let's say after every, I'm just making up a number, after every 1 second, whenever a low priority process doesn't get a chance to run, you simply increase its priority from 1 to 2. So this example makes more sense where you have more than 2 priority levels. Let's say you have 10 different priority levels, right? And the processes which are at the lowest priority level, let's say at the priority level 1. So every time they don't get a chance, they are ready, but they don't get a chance. And when I say they don't get a chance, it means scheduler selects a higher priority process. So what you do is that you increase the priority of that process from 1 to 2. And then again, if it doesn't get the chance, next time when a scheduling decision is made, a higher priority process gets the chance, and the one whose priority you have increased from 1 to 2 is still waiting. So you simply increase its priority from 2 to 3. If it again doesn't get the chance, then 2 to 3, 3 to 4, and so on. Finally, it will reach as 10. So when its priority level will reach, it is now highest priority process, and it will run ultimately. Any question? Okay. So here is a scheduling algorithm which actually combines priority scheduling with round robin. So remember in the previous example, which I did, the two examples which I did on one node, we had two processes D and E having the same priority level, right? And I said that we can select any one of them, like I can select D or E. But let's say if I'm just making up the number, let's say the CPU bus time of D is 100 and CPU bus time of E is 10, right? And if I select D first, now E will be waiting. So E will be waiting for how much? For 100 time units of D before it can run. So it's mean that response time of E will be very high because it need to wait for a longer time. It need to wait for D to complete its execution. So what we can do is that if we end up in a situation where we find two processes or more than two processes having the same priority level, so instead of like selecting any one of them randomly, we can apply round robin algorithm among them to like alternatively select among them. Okay. So priority scheduling can be combined with round robin. Highest priority process is run first. That is just like regular priority scheduling. But if there are multiple processes with the same priority level, they can be served with round robin. So here is an example. Let's say we have processes P1, P2, P3 up to P5. And then we have their bus time 4, 5, 8, 7, 3. And their priority levels of 3 are 3, 2, 1, 3. Okay. So in this example, again, we are assuming that higher the number, higher the priority. Okay. And whenever we need to use the round robin, we will assume the time quantum of equal to 2 time units. Okay. So how this will work? So at time 0, so you first schedule P4. sorry, we are assuming that lower the number, higher the priority. So P4 has the highest priority, so it runs for 7 time units, right? After that, we select the one which has the highest priority. So P2 and P3, they have the same level of priority, 2, 2, right? So we select P2 first. So it has total bus time of 5, right? But we allow it to run, and now we are going to use round robin between P2 and P3. So we allow P2 to run for 2 time quantums from 7 to 9, right? And then we switch to P3. Then P3 runs for 2 time units from 9 to 11. So remaining time unit of P2 is like 3. So it runs once more from 11 to 13. And now remaining time unit of P2 is 1, remaining CPU burst, right? And then P3 runs. So P3 runs from 13 to 15. And now the remaining time unit of CPU burst of P3 is 4, right? Then again P2 runs. So but P2 runs for only 1 time unit because its remaining CPU burst is 1. So it runs from 15 to 16, right? And then we run P3. So from 16 to 20. So now its remaining time unit CPU burst is 2. And then it runs again. P3, P3, P3. So it is running. There is a mistake. There should be another P3 here, another block for P3 because
Because yeah,
each time.
that wouldn't finish. That's only 6 seconds, yeah.
Yeah, there is a mistake. So here it should be another block, right? For P3, and that block will be from 20 to 22. Okay, right? And after that, we are done with P3. Now we pick the process which has highest priority. So we have only P1 and sorry, we have only we have only P1 and P5. Both have the same priority 3, right? So we then use round robin among them, right? So not P1 and P3, P1 and P5, sorry. So we allow P1 to run. So it runs for 2 time units, right? And then we allow P5 to run for 2 time units, then P1 again for 1 time unit. No, for 2 time unit because it has four CPU burst, and then we allow P5 to run again for 1 time unit. Okay. Any questions? So P3 would only run from 16 to 18.
I think the original picture is correct because you have
Yeah.
16
It is correct. It is correct again. Yeah, you are. I just noted it. It is running from 16 to 20, not from 16 to 18. It is correct. Thank you for pointing that out, but it should have a line here, right? 16 to 18 to indicate that a scheduling decision is made, right? So let me just erase this thing because the video is recorded. So if you are watching it later, so you know that it is correct. Okay. Thank you for pointing out. Any questions? Okay. Okay, so here we have an example. Let me check the time. Today you have quiz 2, right? So, okay, here we have an example. We have 4 processes from A to E. You are given their arrival time. You are given their CPU bus time and the priorities, right? So draw a scheduling chart and find the finish time of each process. Use round robin with Q is equal to 5 to schedule the process of the same priorities. So you see here you have processes with same priority level D and D, right? Use preemptive priority scheduling, and again, higher the priority, higher the number, higher is the priority. Okay, so okay, I think let's do this quiz then. Okay, is everyone clear on the question? You are given processes, their arrival time, their CPU bus time, and their priority levels. You need to use preemptive priority scheduling And if two processes or more processes have same priority level, you need to schedule them using round robin algorithm with quantum value or time slice of 5. And you need to find the finish time of all processes. Okay, go ahead and you have 2 minutes. Higher the number, higher the priority. Yeah. Yeah, use that assumption. Higher the number, higher the priority. I can give you 1 more minute. Okay, let's stop it. Let's stop this quiz here. Okay, do you want me to go to OneNote? Even if one student says yes, I will go to OneNote. Yes, please. Okay. Okay. So let me copy this one. Midterm II, page 3. Okay, and we have quantum equal to 5, right? Yeah, we have quantum equal to 5. And okay, let me first write all the information here so that later if you want go back to this OneNote page, you can find the information. Quantum is equal to 5. Higher the number, higher is the priority. And we need to do what? Preemptive priority scheduling. Preemptive priority scheduling. Okay. Okay. So
And this is round robin as well.
yeah, round robin for those processes which have same priority level. Zero, 5, 10, 25, 30. A, B, C, D, E, right? So at 0 only A is available, A is ready, right? So we allow A to run for 5 time units, and then B arrives. So we need to check who has the higher priority, A or B. So A is 3, so A has the higher priority, so we allow it to continue, right? And then at 10 C arrives, so we need to check again between A, B, and C who has the highest priority. Still A has the highest priority, so we allow it to continue, and it finishes at 20, right? So we are done with A, right? So then at 20 we need to make the decision who is ready. B and C are ready, right? So who has the highest priority? B has the highest priority, so we allow B to run. So it runs from 20 to 25, and at 25 D becomes ready. So D has the priority 1, which is lowest. So who is ready now? B and C, D are ready, so B still has the highest priority, so we allow B to continue, and it runs up to 30, and then E becomes ready. So E's priority is 1, which is lower than B, so B continues. So for A, there won't be any bar every time, every 5 time units. Yes, there will be, but I just wanted to, no, there will be no bar, because that quantum is equal to 5 only. Actually, here's the thing. We are scheduling the processes using preemptive priority scheduling. However, if we face a situation where two processes are ready, or more than two processes are ready with the same priority level, then we schedule those processes having same priority levels using round robin with quantum value of 5, right? So at like 5, at when B and C become ready at 5 and 10, they have different priority level than A. A is at 3, has priority level of 2, and C has priority level of 0. Okay. Okay. Yeah. Okay, now let's continue. Where were we? Yeah, we said we allow B to continue until 30, and at 30 E becomes ready. So who is ready now? B, C, D, and E. B still has the highest priority, so we allow it to continue. What is the total bus time of B? 15. So it started at 20, so it will complete at 35, right?
Right.
So we are done with B. Now who is ready? C, D, and E. So the highest priority is D and E. D and E have the highest priority. Now we are going to use the round robin between them. So we and round robin with quantum of 5. So D runs for 5 time units, right? And remaining burst is 10. And then E runs for 5 time units.
Ah, okay. So we cycle back and forth between them?
Yeah, because they have same
Okay.
priority level. Okay, so E runs for 5 time units, 45. So its remaining burst is now 15. Then D runs again. So its remaining time is now 5. Then E runs again, and its remaining time is now 10. Then D runs again. Its remaining time is now 0, and we are done with D, right? Now we check who has the highest priority among C and D. E has the highest priority, so it continues for 10 time units, right? And then after that, only C is left. So C has, it finishes at 90. Okay. Okay, so finish time of A is equal to 20 and B, where did the B finished? Here, 35, C, 90, D, 80. Was it 80? No, 60. It was 60, sorry. And E, 70. Okay. Any questions?
Seems to make sense.
Okay. Then where is this? Where are the slides? Yeah, here. So again, you must be wondering why this solution is different, because this solution again assumes let me put a note here just to not confuse you. Note, this solution assumes, actually it gives you a, you can use it as a practice exercise. This solution assumes lower the number, higher is the priority. So this is different from what I did on my on OneNote. Okay, so don't get confused. That's why you see it has different schedule A, B, C, 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 D, D, and A at the end again. Because here the A is lowest priority. But what I did, I assume higher the priority, higher the number, higher the priority. So the A had the highest priority. So it finished at the start. Okay. Any questions? Okay, so we have seen first come, first serve, shortest job first, shortest remaining time first, round robin algorithm, priority scheduling with preemption and without preemption, right? So now in priority scheduling, what we are assuming, what is the problem with the priority scheduling? Here is the issue. So let me show it on OneNote again. So remember, for example, here in this example, we have how many processes A, B, C, and D, but we are maintaining one ready queue, right? So whenever a process becomes ready, what we were doing it. So let's say you have a head, you have a tail. So whenever a process becomes ready, so let's say you are in this situation, like this is the current snapshot, A, B, C, and then when a process, so tail is pointing toward C, right? When D will become ready, what will you do? You will put the D at the tail and update the tail pointer, right? And when, let's say, E becomes ready, another process becomes ready, you will point tail to the end. So now let's say if this is your current shape of your current state of your ready list, and now you want to pick a process which has the highest priority, right? So what will you do? So these are actually PCBs of processes A, B, C, and D and E in the list, right? So you will go first, so you will start reading the list from the head side, you will check its priority. So let's say I'm assuming that the process which has the higher number has the highest priority. So I will look at the priority of A, and then I need to scan the whole list to find the process which has the highest priority among the ready list of ready processes, right? Everyone is with me? Now let's say assume the situation where this is long, like let's say you have 100 processes which are ready to run, and you need to pick the one which has the highest priority. So you need to scan the whole list of 100 process control blocks, which takes time, because you are scanning, you are doing comparison to find the highest priority PCB. So this is a bad idea, right? It's a bad idea in the sense that it slows down as we need to scan the whole list. So what we can do is that we can maintain multiple queues, right? So what you can do is that you can have a separate queue, ready queue for processes with at the for processes at distinct priority levels. Like for example, you have a separate queue of all the processes which have the priority level of 0. So like T0, thread 0, thread 1, thread 2, up to thread 4. And you have a separate queue, you maintain a separate ready queue for all the threads which have the priority level of 1 and priority level of 2 up to priority level of n, right? So now how it helps? Now let's say if you are a scheduler and you want to find the highest priority process, you don't need to you don't need to scan a long list of the PCBs. You will simply go to the queue of processes where you know that all the processes have the priority level 0. I'm assuming that 0 is the highest number, highest priority level. So I will simply pick the process and from the head and schedule it. So which means that any process from the priority level 1 can run only when the queue of the priority level 0 is empty, which basically means that I have run all the processes and they have finished their completion from the priority level 0. And then only I will go to priority level 1. And if priority level is empty, then I will go to the priority level 2, right? So the good thing is that I don't need to scan the whole long list because I am breaking a longer list into multiple smaller lists, and each list has processes or threads with the same priority level. Am I clear on this? Any question? Like what is the motivation behind having multi-level queue scheduling? Silence mean that everything is clear. If not, please ask. So let me now just
Seems
read
to
this.
make sense. So basically, we just store them based on priority
Yeah.
in
So we
multi-levels.
have, yeah. We just have separate queues for every priority level. So in case of a single queue holding all the ready processes, the scheduler needs to scan the whole queue to find highest priority ready process. And it is like the time to scan increases with number of the PCBs or process control blocks in the linked list or ready queue, right? So what we can do is that ready queue is partitioned into separate multiple queues, just like shown in this figure here. So, okay. Now scheduling must be done between the queues as well, which means that between the queues mean that uh, when I, for example, one option is, as I explained earlier, that processes from the priority level 1 can run only when all the processes from the priority level 0 they have completed their execution and the ready queue of priority level 0 is empty, right? So this is known as fixed or strict priority scheduling. That is, first of all from the priority queue 0 and then from priority queue 1 and so on, right? However, this can end up in a situation where some processes face starvation. Like for example, if I am, let's say, lowest priority level is 100 and there are some processes waiting at priority level 100, but all the time system or users keep generating processes with priority level greater than 100, like let's say anything between 0 to 99. So as long as there is a process with a priority level of 0 to 99, the processes sitting in the lowest priority level queue, like 100, will never get a chance to run, right? So yes, we can solve this problem by aging, as I explained earlier. But another option is, like, instead of doing fixed or strict priority scheduling among queues or between the queues, we can use the time slicing, which is that we assign time to each queue. So each queue gets a certain amount of CPU time which it can schedule among its processes. For example, let's say we can say, okay, we will assign 20% of the CPU time to the priority queue 0 in round robin. Like let's say we give 20% time, and in 20% time it doesn't matter how many processes it can complete, but if there are like more than one, it can use round robin among them, like between T0, T1, T2, and T3 and T4, right? So scheduler will spend 20% of the time on scheduling the processes from priority level 0, and then let's say we assign 10% time to the priority queue in FCFS, right? So again, there are two levels of scheduling happening here. One, how the decision is made in picking the processes from different queues. So first approach is we do the strict scheduling. Like if the upper queue is not empty, we cannot move to a queue of lower priority. This is one option. The second is we assign time slice to processes sitting in each queue. So like we assign 20% time to schedule the processes in queue of the priority level 0, and then 10% time to the processes sitting in the queue of the priority level 1, and so on. But that even within that 20% time, which is, let's say, assigned to the processes of priority level 0, how we make the decision among the processes of the same priority. Either we can, it is up to us. We can say, okay, we will use round robin among them if we are interested in increasing the response time, right? But we know that round robin is good at reducing the response time, but it is bad at reducing the turnaround time, right? So, but let's say if we are not interested in reducing the response time, but we are interested in reducing the turnaround time, we can say, okay, we will use first come, first serve for those processes which are sitting at the same priority level queue. Any questions? So that's why there is just in this example like 20% to priority queue in RR and 10% to priority queue in FSFS. So FCFS. So this is not like, a hard, fast rule. It depends upon what is your requirement. Any questions? Okay, so this is just an example of a situation and a case where you can apply this multi-level queue scheduling. Let's say in your system, you have 4 different type of processes or 4 different categories of processes. So there are some processes which you are treating as real-time processes. Real-time processes mean that they need to finish their execution at strict time points. Like, for example, these are critical applications which you are running and you don't want to delay them. So you are putting them in the category of the real-time processes. And then you have another category where the processes are system level processes, which mean that these processes are launched by the kernel or the operating system. Then there are some other processes like which are user level processes, but they are interactive, which mean that they are performing lot of IO operations, for example, writing to files, reading files, writing to screen, writing to printer, and so on and so forth. And then there are some other processes which you are naming as batch processes. So these processes are also user level processes, but they are not interactive. So they are doing something, but they are supposed to do it in the background, right? So for interactive processes, we are more interested in, we want them to run more quickly, right? So what we are going to do is like, we can assign the separate level of priorities for each process category. So we can assign highest priority to the processes which are real time, then next highest is system processes, then next highest is interactive processes, and lowest are the batch processes, right? And we can put them, so we have 4 priority queues, and a process of a particular type goes to a process of a particular type goes to its own category or into its own queue. So for example, a real-time process will go to the highest priority queue, an interactive process will go to the third queue, and so on and so forth. Okay, let me start with this. And you have a quiz? No, you don't have a quiz today. So we have time, right? You don't have a quiz. Let me check the syllabus. Yeah, I don't have quiz. Okay, any questions before we go to the next subtopic? Okay, so before we go to the next topic, just note here that if a process in this multi-level queue scheduling, if a process, for example, enters in real-time process queue, or maybe this is better example to explain. So in multi-level queue scheduling, let's say if a process or a thread, let's say T5 enters in priority level 2, right? So let's say I'm putting it here, T5, right? Because it has the priority equal to 2. So for during its lifetime, now it will never change its priority and it will always stay in the same queue. Queue which corresponds to its priority. For example, T5 cannot move to the queue priority level 1 queue or priority level 0 queue or priority level 3 queue, right? Which mean that priority assigned to a thread or a process is static, right? So the next thing which we are going to cover is multi-level feedback queue, which is different from multi-level queue scheduling. In what sense? In the sense that here we allow a process or a thread to dynamically move among queues depending on its priority. So which basically mean that priority of a process is updated depending upon situation, right? What situation I will explain. But the point here is that as compared to the multi-level queue scheduling, multi-level feedback queue scheduling allows a task or a process to move around or move among queues by changing its priority dynamically. So let's have a try to understand it through an example. Let's say we have 3 queues, right? So Q0, uh, so Q0 is like our, let's say, highest priority queue. Q0, Q1 is next highest priority, and Q3, Q2 is lowest priority, right? So so all the processes which say let's say which have priority of 0, they will go to Q0. All processes with priority level 1 will go to Q1, and all processes with priority level 2 will go to Q2. Okay. Now RR with the time quantum 8 millisecond. What does it mean? It means like since all the processes with priority level 0 will go to Q0, it's mean that you can have here multiple processes, right? Let's say 10, you have 10 different processes. So what you will do is that to schedule those 10 processes of having same priority level, you will use round robin scheduling algorithm to alternate among them, right? Similarly, for all the processes sitting in queue of the priority level 1, you will use again round robin, but with a quantum of 16 millisecond. For Q0, you are using 8 milliseconds, right? And for all the processes which are sitting in the queue of the priority level 2, you will use first come, first serve. Okay. So so how in this example, how the scheduling algorithm is working is as follows. So whenever a new job will enter Q0, which is served using round robin with a quantum of 8. So when it gains the CPU, job will receive 8 millisecond. So let's say if you have, let me try to give you an example. Let's say you have process A, and process A has priority of 0. So it will enter into the Q0, right? So when it will be turned off process A to run, it will be allowed to run on the core or on the processor for 8 time units, right? So now we don't know what is the CPU burst of the process A, like how long it takes to complete its execution. We don't know. So if it completes its execution in one quantum of 8 unit, fine. But if not, it's mean that its execution time is greater than 8 time unit. So we will move it into the Q1, which means the lower priority. We will change the priority. So PA will move from Q1 to Q2, right? Not Q2, Q1. Okay. Because it was not able to complete in 8 time units. So what is our motivation behind having all the processes with which can complete within with a quantum of 8 time units in the highest priority queue to increase the throughput? Because if these processes can complete earlier, so because they have smaller total execution time, they can complete earlier, and as a result we can have more number of processes or thread completed per unit time, So we can increase the throughput of the system, right? But if there is a process which is taking more than 8 time units, it means that it is taking longer. So if it is taking longer and if we keep it in the Q0, it can affect, the completion time of other processes because it will be incurring more context switches. So what we can do is that we can move it to the Q1. In this way, we will not be affecting the throughput of all the processes which have which have the execution time of less than or equal to 8 time unit, right? So when we move it to Q1, so at Q1, job is again served and receives 16 additional milliseconds. Now a PA will enter in this queue, and when again remember, uh, Q1 is again using RR to alternate between all the ready processes in Q1, right? But with a quantum value of 16. So when PA will get its turn, it will be allowed 16 time units. And if it gets completed, we don't know how long it's again, we don't know how long its CPU burst is. So if it gets completed in additional 16 time units, so fine, we are done with it. So which mean like, let's say 8 plus 16 because it's consumed 8 here and 16 time units here. So it gets completed in 24 time units. We are done. We are fine. But if not, we can now it's mean that it is a longer process, right? So we cannot allow it to block. We cannot allow it to create the convoy effect. Remember the convoy effect from our previous lecture? So it can possibly be a longer process which is taking longer time. So what we can do is that we can move it to the Q2. So we are effectively reducing its priority level, right? So now what will happen that it will be moved to FCFS, and now here it will be served as first come first serve. So if it still does not complete, it is preempted and moved to the Q2. At Q2, jobs are served with first come first serve. Okay, so this is like a very flexible scheduling algorithm where, depending upon the characteristics or feature of a process, you can, for example, the CPU burst time, you can basically move around a process from one queue to another queue. But again, here we are only moving like from higher priority queue to the lower priority queue. There can be also a situation where you can move a process from a lower priority queue to the higher priority queue. For example, let's say if a process is sitting here in Q2 and what we are doing is that we are saying, okay, if we will serve all the processes in the Q0, but some process sitting in Q2 and it never gets a chance. So we can simply increase its priority and move it to the Q1. Again, if we can put some time limit, and if within that time limit it never gets a chance to run because there are still other higher priority processes, we can increase its priority level and move it to the Q0. Okay. Any questions? Okay, we have 1 minute left, so let me just read this slide. It is the same slide, but I just like from the previous one, but I first wanted to show you the example and then walk you through this, theoretical part. Okay, is there a question? What topic will the midterm cover? Is it from chapter 4, thread, and chapter 5 to chapter 4? Okay, I will answer this. Just let me finish this slide. Only this slide, okay? I will answer your question. So in multi-level feedback queue scheduling, a process can move between the various queues, just like I showed you. Aging can be implemented this way. So a specific multi-level feedback queue scheduler is defined by the following parameters. So like, as I said, this was just an example, right? But by defining different parameters, you can develop different algorithm. For example, what are those parameters? Number of queues. Here in this example, we have only 3 queues, right? Scheduling algorithm for each queue. Here we said that the first queue is 0 is using round robin with quantum of 8, second using round robin quantum 16, third is using FCFS. But if you change those algorithms, let's say you say this one is using shortest job first. So it's mean that overall you are developing a new scheduling algorithm. Method used to determine when to upgrade a process. For example, here we were using like if a process is able to complete its execution not able to complete its execution in 8 time units, then move it to the Q1. So that was a like method. So similarly, if you change that method or criteria, it's mean you are developing a new algorithm. So method used to determine when to demote a process, like from higher priority to lower priority, or when to move from lower to higher, right? Method used to determine which queue a process will enter when that process needs service, right? So when initially at the start of its life, when a process becomes ready, will it go to the Q0 or Q1 or Q2? And what is your criteria to decide that? Okay. So with that, let me stop here and try to answer your question. So here is this question from a student. What topics will the midterm cover? Is it from chapter 4, threads and concurrency, to chapter 5? Okay. Yeah. So, okay, let me answer that by looking at the syllabus. So we had midterm at 0930. So it will be whatever we have covered after midterm 1 exam, starting from 10/02. So 2nd of October to 28th of October, not today. Okay, so the material which we have covered today, that will be not part of the exam. You are not responsible for that. But before that, whatever we have covered until last Tuesday, that is 10/28, you are responsible for that. Again, I will also make an announcement, but just to make it clear here for you. So from 2nd of October to 28th of October, whatever we have covered, you are responsible for that. Any questions?
Practice exam will be posted, right?
Yeah, I will release the practice exam and also its solution.
Okay.
Anything else? No? Okay, then prepare well for the exam and good luck. Is it the same pattern like the first exam? They're more or less same, but I don't want to, how to say, limit my flexibility in the sense that because we have new materials, so the maybe the difficulty and the type of the questions will be different definitely as compared to the first exam.
Can you hear me?
Yeah, I'm here. Yes, go ahead.
Yeah. So what I really want to know is like it's not something like list this other stuff. It's just like the application of what we have been doing, right?
Yeah, there can be some like, short answer type of questions, but like, for example, I don't know in midterm 1 if we had some, let me check. Let me check. Uh, Yeah, so you had these true false type of questions. So possibly, I'm not saying, I'm not granting, but again, they can be there. I don't know. I haven't yet prepared that final exam, so midterm 1 exam, so I don't know, but they can be there. And also, were there any other descriptive questions here? No, right? No, but I mean, there can be some short answer type of question, like, okay, for example, uh, uh, I don't know. I mean, when I will look at the slides, it will come to my mind. How can I give you an example? So, for example, what is the difference between concurrency and parallelism? I know we covered it before the midterm 1 exam, but I'm just giving you an example, right?
Okay.
Yeah.
Thank you.
I will not require you to write a paragraph about something, just 1 or 2 sentences.
All right. Thank you.
You're welcome. Anything else? No? Okay, if not, then I'm signing out and good luck to everyone.
Thank you.
You're welcome.